All right. So, hello, grade 12 college and grade 11 university chemistry students. This video is actually for both my grade 12 college and grade 11 university chemistry class. I've mentioned before that in the first 3 units of those courses, there's actually a lot of overlap. So this lesson is identical for the grade 12 college and grade 11 university chemistry students. And so this video is for both groups. In units 4 and 5, in those courses, there's no more overlap. So those units are completely different. But the first 3 units are quite similar. And in particular, this third unit that we've now started is actually basically identical in both courses. And we're at the same point for both groups. So this is a video for both my grade 11 university chemistry and grade 12 college students. And this video in particular is actually just a quick review of what you had learned about on Friday. So Friday's work was asynchronous. I just posted a couple of handouts for students to work through. And since schools are now closed again on Monday, I thought it would be helpful for me to just record a video where I explain what you had learned on Friday. And then there's going to be another video where I'll explain today's material. So I've become a bit of a YouTuber. This is just a YouTube video that you can access on YouTube. And so yes, let's just talk a little bit about what you had learned about on Friday. This handout is from Friday's material. It's called Converting from Moles to Number of Particles. So in this video, I'd like to just take some time to review this material from Friday. So let's just begin by backing up and just reminding ourselves of what a mole is, because we had learned last week what a mole is. So we learned last week that if you have a mole of something, that means that you have 6.02 times 10 to the 23 of those things. Now, to be clear, that's a very, very big number. We've reviewed how scientific notation works. So 6.02 times 10 to the 23 basically means 6.02 multiplied by 10, 23 times. So said out loud, this number is 602 hexillion, which is an extremely large number. And we learned a bit last week about why the number is so large. It's so large basically because this number is used to count atoms and molecules. And atoms and molecules, of course, are very small things. So whenever we're measuring numbers of atoms and molecules, that number is going to be very large. Now, as part of today's material, I included a fun reading for you to do. So I just thought I'd talk about this reading briefly. This reading is an excerpt from a book called What If? Serious Scientific Answers to Absurd Hypothetical Questions by Randall Munroe. As the title of the book suggests, it basically just gives legitimate scientific answers to questions that are completely absurd. I don't know if anyone reads science books for fun, but it's an entertaining read, I think. I would recommend it to anyone who likes just reading about science in their spare time. And this excerpt is taken from the book. One of the readers submitted a question asking, what would happen if you were to gather a mole, unit of measurement of moles, the small furry critter, in one place? Okay, so they're basically asking if you gathered 602 hexillion moles, the furry critters, in one place, what would happen? And it's just kind of a silly reading, right? The answer is that things get a bit gruesome. So one of your tasks is to just read through this reading for fun. I won't go through the reading, but the answer basically is that if you had 602 hexillion moles, as explained in the reading, that amount of moles would actually be slightly larger than the moon. And so it gets into the science of what would happen if you actually had an amount of moles that large, slightly larger than the moon. So it's just kind of a silly reading for you to go through to start off today's stuff. Okay. So yes, the point of this video, again, is to just review the material in this handout on converting from moles to number of particles. So again, if you have a mole of something, that means that you have about 6.02 times 10 to the 23 of those things. And I will explain again in the next video what's so special about this number. But for now, we're just going to roll with it. So when you have a mole of something, you have 6.02 times 10 to the 23 of those things. Okay, so for example, if you have a mole of water molecules, that means that you have 6.02 times 10 to the 23 water molecules. So that's 602 hexillion water molecules. Now, if you instead had 2 moles of water molecules, how many water molecules would you have? Well, that's a pretty straightforward calculation, right? We've said that if you have 1 mole of water molecules, you have 6.02 times 10 to the 23 water molecules. So how many water molecules would you have if you had 2 moles? Well, it would just be twice that number. So it would be 2 times 6.02 times 10 to the 23. And so if you type this into your calculator, 2 times 6.02 times 10 to the 23, the answer comes out to be 1.204 times 10 to the 24 molecules. So that's how many molecules of water you would have if you had 2 moles of water molecules. Now, when we worked this out, we actually did our first calculation using the mole. And if we want to express an equation to help us calculate the number of molecules, the equation would look something like this. So the number of moles is denoted with a lowercase n. So in this problem, the number of moles was 2. We were asking how many molecules would you have with 2 moles. So that's a lowercase n. And then 6.02 times 10 to the 23. This is the number of particles in a mole. That is often denoted with a capital N with a capital A subscript. And a capital A subscript is chosen because this number is often called Avogadro's constant. It's named after an Italian scientist with the last name Avogadro. So N sub A is the symbol for this constant, 6.02 times 10 to the 23. And then in this problem, we calculated that the number of particles was 1.204 times 10 to the 24. And so in calculations, we denote the number of particles with a capital N. So in performing this calculation, we multiplied the number of moles by Avogadro's constant, and that gave us the number of particles. So this is the relationship that we made use of. We multiplied the number of moles by Avogadro's constant to get the number of particles. Now we can equivalently write this relationship in terms of the number of moles, as we often do in chemical equations. So if I just solve for the number of moles and write the relationship in terms of the number of moles, I would get this relationship. Okay, so we have the number of moles equals the number of particles divided by Avogadro's constant. And so this handout gave you an opportunity to put that equation to use. In the handout that I provided, there was just blank space on the page for students to write the answers. And so in your copy of the handout, for those of you that got a copy on Friday, there is no writing here. It's just blank. So the idea was for you to write down the answer that I've written to just see how this works. So in our first example, we're making use of this relationship. It says a commercial product that people sometimes take to settle an upset stomach contains magnesium hydroxide, MgOH2, a base. If a teaspoon of stomach medicine contains 4.1 times 10 to the 21 formula units of magnesium hydroxide, what amount in moles of magnesium hydroxide is in the teaspoon? So in this example, the particles that we're dealing with are formula units of magnesium hydroxide. This is a bit different from what we had seen earlier in the handout, where the particles were molecules instead. So again, it doesn't matter whether the particles are molecules or formula units. The idea is that if you have a mole of something, you have 6.02 times 10 to the 23 of those things, whatever those things are. So if you have a mole of water molecules, you have 6.02 times 10 to the 23 water molecules. If you have a mole of magnesium hydroxide formula units, then you have 6.02 times 10 to the 23 magnesium hydroxide formula units. If you have a mole of basketballs, you have 6.02 times 10 to the 23 basketballs. So a mole is simply 6.02 times 10 to the 23 of whatever things we're talking about. So in this problem, we're dealing with magnesium hydroxide, which is an ionic compound. And we've said before that the units in an ionic compound are called formula units. So 1 unit of MgOH2 is called a formula unit. It's technically not a molecule. So we've talked about that before. So yes, the question is, if in a teaspoon of stomach medicine, you have 4.1 times 10 to the 21 formula units, what amount in moles would you have in the teaspoon? And so to solve this, we just make use of the relationship that we saw earlier. Okay, so the relationship is that the number of moles equals the number of particles divided by Avogadro's constant. Okay, and so in this problem, the number of particles, which in this case are formula units, is 4.1 times 10 to the 21. And so we divide that by Avogadro's constant, 6.02 times 10 to the 23. And the answer comes out to be 0.0068 moles, which we can also write in scientific notation as 6.8 times 10 to the minus 3 moles. Okay, so this is just making use of the relationship that we saw earlier in the handout. All right, so let's look at another example. This one we'll see is slightly different. We're not solving for the number of moles. We're instead solving for the number of particles. So this question says hydrazine N2H4 is a versatile compound that is used in pharmaceuticals, rocket fuels, and airbags. Suppose that a chemical sample in an airbag contains 3.65 moles of hydrazine. How many molecules are in the sample? So in this example, we're not actually solving for the number of moles. So we're not solving for this lowercase n. We're instead solving for the number of particles, which in this case are molecules. So we're solving for the number of molecules, capital N. And so in the first step, I'm just solving for capital N. I'm solving for the number of molecules. And to just be clear about what I'm doing, maybe I'll just rewrite it at the bottom here. So the relationship, again, is n, lowercase n, equals uppercase N over Avogadro's constant. Now again, we're not solving for the number of moles in this problem. We're solving for capital N. And so I want to get capital N on its own. And so to do that, I need to multiply both sides by n sub a. So if I multiply both sides by n sub a, then the n sub a's cancel on the right side. And so that gets me the capital N on its own. And so if I just rewrite another line showing what capital N equals. So we have capital N equals lowercase n times n sub a. Okay, so that's what's going on in the first two lines. I'm just basically solving for the number of particles. Okay, so yes, in this problem, the number of moles is 3.65. And then Avogadro's constant, of course, is 6.02 times 10 to the 23. So if you have a mole of molecules, you have 6.02 times 10 to the 23 molecules. So if you just multiply it out then, the answer comes out to be 2.20 times 10 to the 24 molecules. Okay, so this lesson is really about converting from moles to number of particles and vice versa. So being given the number of particles and finding the number of moles, or vice versa. Okay, and then you'll see that there is an opportunity for you to try out some examples on your own. So hopefully you had an opportunity to try that on Friday. But if you didn't have an opportunity, I would say now would be a good time. Okay, so all of these questions involve determining the number of moles given the number of particles, or vice versa. So it's the types of examples that we saw in this handout. Okay, so that's just a review of Friday stuff. In the next video, I'm going to talk about today's stuff, which is about converting from moles to mass instead of from moles to number of particles. So that's our next video.